Thank you for the introduction. Thank you all for being here. Maybe I'm going to wait for a few more seconds till everyone's seated. I hope you all had a good coffee break. Today, I'm going to talk about building batch pipelines with Python and DuckDB. And the assumption here is that we are having raw TCP streams as our data source, which is probably not the most common case anymore, but is still highly relevant, as we will see throughout the talk. Before we start, to get all the brain juice flowing, I have a few questions for you. Just raise your hand if you see yourself in the answer. So who in the room builds data pipelines for a living? Almost all of you, I think. Who does that in the cloud? Roughly half of the people raised their arms. And who of you who do data pipelines in the cloud process less than 100 gigabytes per day? I think that's almost everyone. Okay, so today I want to show an alternative that might be useful for some cases. But who am I? My name is Orell. I'm a data engineering consultant, and I basically build data pipelines for tech products, tech companies, usually small to medium-sized enterprises. And I have about 7 years of experience, like professional experience with Python. And if you want to contact me afterwards for questions or anything, you can find me on LinkedIn. And also my email address is up there too. So you can send me an email if you have any questions, want material or something like that. So before diving into the meaty part of the presentation, what are we going to do today? I already did the introduction. Now we will talk about the pipeline design, a little overview, then we dive deeper into ingesting TCP streams, data validation, and also storage requirements. And last but not least, we will talk a bit about orchestration of the whole thing, but this will not be the focus of the talk because it wouldn't fit into the 40 minutes that I have here. And at the end, we'll have a small outlook to things that we should or could do in the future. Short disclaimer, I don't hate the cloud. The talk kind of feels like that maybe, but I see there is a lot of potential use cases and use cases. But I also think that the cloud is not always the best solution, especially if you're just starting out. Building data pipelines, and a lot of my clients, they have little data infrastructure in place and little cloud know-how, so it's probably not the best to go all in into cloud systems. And also, a lot of data systems, as we just saw by you raising your hand when I asked who processes less than 100 gigabytes per day, probably do not need the cloud scale in your day-to-day life. And also, using the cloud does not make you modern just by using the cloud. That's also something that I kind of see every now and then, that people think we use cloud, we are now all digital and modern, and everything is better. So what will I present? I will present a, let's say, pragmatic approach for a specific class of data systems, mainly if their data is coming in through TCP streams. And usually with systems that provide out data by TCP streams, like raw TCP streams, we do not have control of the source, because that's usually some kind of embedded system, machine in some industrial shop or something like that. And usually, unless you want to hack the firmware or the supply of the machine changes the software for you, you do not have control over what's happening there. And we will use Python and DuckDB for simple but effective pipelines that I have used before in production that work quite well. So, coming to pipeline design. Basically, this is the situation we're facing. We have a few sources. Usually with raw TCP streams, we do not have thousands of sources, but a selected few, maybe a few handful, so in the low tens, I would say. And they're all sending TCP streams to a black box that we will cover throughout the talk. The black box does something, and then at the end we'll have the users. And who are the users? It's basically everyone who needs the data that we are ingesting and storing. So it's oftentimes business intelligence, it's ML use cases, it's reporting, dashboards, observability sometimes, especially if you're doing like work in an industrial setting, you want to know what your machines are doing. That kind of situation is what we're talking about here. The question now is what's in our black box? Any ideas? Yeah, it's our data pipeline. So this is what we're going to talk about most of the time. And what does it look like? The data pipeline in general has 3 components, basically. It has some ingestion. It does oftentimes have some pre-processing because data that comes through raw TCP streams is not exactly the cleanest data around. And some kind of storage is also required to obviously store the data for future analytics. So this is the situation. TCP streams as data sources. Then our pipeline has ingestion, validation, storage, data management, some processing, and we also have consumers that consume the data that we are processing there and storing. First, the data sources. TCP streams seem outdated maybe, at least raw TCP streams, but in many, again, in many rough environments in manufacturing, shop floors, embedded systems, we still have them around, and they are around because that's sometimes what was available like back in the day, and usually machines in manufacturing, they are not built to like break down after 3 years. It's not a consumer product. They usually like last quite a while. So all these like maybe outdated data sources are still around in many places, and that's why they still matter. We have to deal with that, and now with all like the Gen AI hype, a lot of companies also feel like they need to do more in the data space. They want to build products around data, and then they have the data like being generated, but they're not doing anything with it. So we have to provide basically an interface for them to process the data. A TCP stream, as you probably all are roughly aware, is basically a continuous flow of bits and bytes. It's zeros and ones, they just come in. Depending on the source, it's some kind of semi-structured or structured message. If we're lucky enough, we have like new line delimited messages that we can relatively easily parse when we deal with that. Examples would be sensor readings from some factory machines, for example, operation logs sometimes too, but also legacy telemetry from like equipment in the field. Today you would probably use different technologies for most of these cases, but they're still around, so we still have to deal with them. The requirements here are that we need to convert these raw TCP streams into some kind of batch data sets for analytics, because we don't want to deal with the stream itself. It also is kind of a batch, even though it comes in a stream, like messages are still coming through a batch. It's not like a continuous, unseparable flow of bits and bytes. We still can do something with it. Also, batch processing is much easier like in the later stages of our pipeline. And most of the time when people like ask for stream real-time analytics, it's good enough if the data is ready for the next board meeting. So it's usually not an issue, and if people like want that, there should be a good reason for it. And we still have some like good, basically almost real-time characteristics there. We also shouldn't drop data. That is actually quite tricky with TCP because we don't really know when we drop data, only the source knows usually. And there's no persistence in TCP, so there's no output and input buffer. And when we are too slow ingesting our TCP stream, we will inevitably drop data along the way. So the challenges are that we have no inherent replay or persistence in the TCP stream itself. For example, if you would use like some Kafka broker or something like that, you would have some buffering in between. We have very variable message formats. So it's there are no standards in like what you send over TCP streams. It's just bits and bytes. And this also requires us to have some kind of custom ingestion before we do any batch processing. And again, we do not control the source, so we do not have any chance to change the way our TCP stream looks. Okay, now coming to the ingestion. Again, we want to ingest data from TCP streams. And first, we need to ask ourselves, what does our data actually look like? And this is basically the core question with data modeling. What does our data look like? And the general challenge is that we receive bytes of some kind, and we need to do something with it in order to give it a meaning. Otherwise, it's just zeros and ones, and if we don't give it a meaning, it's basically useless for us. We don't control data generation, again, and however, we can control the ingestion. So what we are doing with the data is still up to us, because we can control what we are basically getting ourselves into. As I said before, there are many different data formats. For example, we can send JSON, we can send byte strings. That could be JSON byte strings, for example, but could be something completely different as well. Or what also happens quite often, we have proprietary formats. These are usually the trickiest one to get right, because you need a lot of custom parsing and code for that. And depending on how much data you get, Python might not be the best way to do this, because the parsing is something that is quite taking a long time, so you want different things there. However, no matter what our data looks like, we need to understand and model the data that we receive in order for us to do something with it. Because otherwise, we'll just save bits and bytes, and we can interpret them later. But we also don't want to have a super degraded data quality right from the start. So in Python, the go-to for modeling data in that way is probably Pydantic, although there are other options around. I think the most prominent alternative would be MessageSpec. But what we are doing here is we use the Pydantic base model to model the way our data looks. For this, we just import the base model. Then we define some enums that are basically literals in our system now. And then we define these classes that have basically the data types and the name of these data types, the name of these variables and the data types of them, in order for us to do basically the parsing and validation out of the box. This is kind of what Pydantic gives us, at least for JSON data. So this is what it looks like, and this is very powerful if you're dealing with any kind of JSON data, no matter where they come from, because it makes it very easy to give your data some meaning and also allows you to reason about what's happening in your code. So data modeling is kind of the first step towards data validation. If we don't have any model of our data, we can never say if our data actually looks like it should look, because what are we comparing against? And data modeling is also useful for another reason. We have to reason about our system. Thinking about the data types and the data that goes into our system actually forces us to think more thoroughly about what we are doing with the data, what boundary conditions we might face in the long run, and all that kind of stuff. And I think that is quite important as well. Although in practice, this is one of the steps that's often neglected, I would say. But why do we need data validation? We want to ensure that our data has some quality. We don't want to ingest data that is not matching our standards, at least not in the same place that we put all the other data that we consider to be good or valid. So what I would usually do is basically split the stream already in good and bad data if you want it. And this also helps to spot more systemic issues, because in TCP streams, once again, there's a lot of different problems that can arise also from older machines. For example, data encoding, stuff like that, where okay, I can deal with that, or I can't deal with that, and you can try to work around these problems in the later steps. So what Python or Pydantic in this case also allows us to do is validate JSON data against this model we just defined by using a type adapter and validate JSON. We could also directly use the class, but this is more performant in the long run. So we'll want to do this because usually in TCP streams you also ingest a lot of data and you don't want it to be the bottleneck of your pipeline. So we first define the type adapter, which is basically the tool that we want to use to validate our data, and which is basically this. We just call validate JSON on our JSON data, which is a string. And then the output is basically a Pydantic model, and we can just access this with the typical attribute accessors. So we don't have to do dictionary accessing kind of style, and this is much more user-friendly. It's more readable in many ways too. So the ingestion basically should do two things. It should persist incoming data to the storage unit that we're having, and also validate the data against our model, so we can be sure that there's only good data basically coming into our system. So this is kind of what we're talking about now. These are the two steps, and we have two general options to do this. We can either write before we validate, or we validate before we write to storage. Depending on what kind of system you have and the amount of data that you're dealing with, each of these approaches has their merits. Okay, now we talked about what we can do, but let's talk about the actual ingestion now. We have TCP streams. What do we need for the ingestion? Any ideas in the audience? Okay, a TCP server. It's basically just as simple as that. There's not much to it, at least not conceptually. And it's just running a TCP server and not much more. The next question that we're facing, do we want to do this synchronously or asynchronously? And just for fun, let's do async here. Why async? Because it's supposed to be fast. But for real, async I/O is great for input-output operations, especially with networking. You get the most bang for your buck, basically. And also, our ingestion has two input-output operations. It takes inputs from the network, and it needs output to the storage. Whatever our storage looks like, that is something we will discuss here in a minute. If you're more interested in async, I can highly recommend these three talks. They're all on YouTube. They go into more detail on kind of what to think about, because it's also very easy to basically destroy your performance with async as well. Probably, if anyone here has deployed some kind of fast API app, they probably ran into this issue at some point. Okay, I still see some people taking pictures. Okay, good. So in the async versus sync debate, we decided to do async. Running a TCP server, we create our own class for that because we want to encapsulate a few different operations. But what we need is basically a host and a port, and then serve the TCP server. And because we're doing async, we need to await the serve statement. The serve is basically using async I/O to start the server, and with the self.handle connection, we give it a function that it should run for each connection that we are basically making on this socket. And that's kind of all that is to starting a TCP server. What we now need to do is we need to kind of implement the rest of the class to make it work in a way that makes any sense. So for this, to instantiate the class, we need the host and the port, then have some data source type that would make sense. For example, if you would start a different server for each data source, or source type, which usually makes sense because you want to differentiate between different data types. And it also allows you to kind of scale out your ingestion for different kind of types of data. And depending on the data, we also do different or create different type adapters. We also have a buffer. I think that is something that is highly recommendable because we do not want to write to disk or storage, whatever that is, for every incoming data set, because writing to disk or to S3 storage database actually takes quite a bit of time, and we want to buffer in between so we get more performance out of it. The buffer size here is 1,000, but that is something that you kind of need to figure out for your system parameters, because it's very depending on what kind of data you have, how much basically memory you have on your machine, and how quickly you can actually write to your storage. And because we also want to do this, we also have a async batch writer here that is also just another class, but we, like, in a nutshell, it writes asynchronously to storage whenever the buffer is full. And then this is basically the meat of the whole TCP server. You want to handle connections when connections are made. And for this, we're doing basically just a loop until the connection is closed. We want to read until the loop is closed, and then just read one line of data. And we, again, do this asynchronously because we're doing async. So when no data is coming, we can do different or other things than just waiting for the data. If you wouldn't do this asynchronously, you probably have to go like threading or something like that, and usually that's kind of a pain too. After we received our data, we validate it against our JSON or against our Pydantic model and receive JSON data out of it. We then extract the timestamp, if there's a timestamp, but we in general can extract some parameter of the data, for example, to partition later on, and then we add it to the batch that we are, or to the buffer where we want to write to disk later on. So the timestamp here is being used for partitioning, but that is kind of like abstracted away in the async batch writer. But usually some kind of partitioning is required if you want to go from streams to batch, because you need to kind of have units of data that you can work with. And this is basically where you do all your data logic. Here we also do some minor error handling, so whenever the data is not good enough for our model, we just write to the std error and continue with the loop. So we just go to the next. What you could also do here is that you can basically save bad data, if you want so, to a different place. So you can look at it later on, for example, to understand if the problem is in your data transmission, or if the problem is with the machine itself, or what kind of problem you're actually facing. So the takeaways here. Data modeling is important. With like all the talks I give and all the projects I work in, this is usually what I stress the most, because it gives you the most, especially with like the dynamic typing nature of Python, it gives you the most impact and quality of your code. You can do data validation that builds on top of this data modeling. If you have any kind of JSON data, Pydantic is a very good choice in my opinion. Also, I think validation before writing is the better approach if performance allows for that, because you can deal with validation and data quality issues like as early as possible, and you don't have basically bad data in your system. Although that's probably an like opinion, and I would say there are different approaches to this. And if you are like running at the very like boundary of your performance, I would also consider async just to get the most out of your system. Okay, coming to storage next. This is all we had as of now regarding our storage. It doesn't say much about the actual storage itself. It's just some abstraction, and it keeps basically track of some buffered data, and whenever enough data is ready to be written, we write it somewhere. So when we're talking about storage, the bottom part of this picture is basically what we're talking about. So we have some raw data that we store. We might have some pre-processed data. We might have even some more processed data later on, or some transformations that are already happening. And for things to consider, we could, for example, use our raw data storage right on the disk. So if you're like an on-prem server, why not just write to disk? It's usually the quickest of the, let's say, realistic options. Pre-processed data, for example, could also go to the database if it's, let's say, suitable data for the database. We could also write both of these files or of these data things to the disk, or use database for both. It kind of depends on the nature of your data, on the performance requirements and performance boundaries that you're facing in your system. But I'm a big proponent for writing at least raw data to storage first, because that gives you the most flexibility later on. So in general, we have different options like the local file system, blob storage. This is also something that I would consider a very good use case for cloud, even in this scenario, because it kind of gives us unlimited space. We could use a database. That depends on the kind of data that you're working with. But if you're going file system, I can also highly recommend FSspec for more flexibility as you scale. So you can first say, okay, we ingest a couple, I don't know, gigabytes per hour. We can write this to disk and deal with it later. As your system scales, you might want to also do this in an S3 storage right away. And FSspec is basically a pretty cool abstraction on top of that. So you can have one API for different types of storage. I can also highly recommend the talk by Einat Orr and Barak Amar on this year's PyCon in Darmstadt. I don't think the videos are out yet, but when they come out, you can watch that. It's also a great intro to that. Okay, let's say we decided to go file system here, because we want to keep it simple, and we do file system first and then go from there. Everything else we can deal with later on. The advantage, we have very low latency because we have no networking. There's no network traffic involved at all. Usually if we have some kind of server, we do have a file system ready somewhere. It comes at no extra cost usually, and we have no data transfer, which usually also kind of can raise costs if we're dealing with like different cloud providers, for example. The problem is it's very limited, like in space, for example, like on a server, even if you have a few terabyte of SSD space, for example, you still run into problems quite quickly for modern scale data pipelines, even if your data is comparatively small. So we need to take a closer look into the whole storage pipeline, I think. And this is the part we're now looking at. So we have the ingestion already taken care of. We don't talk about the pre-processing, but about how do we store data. And basically, it's about storage and validation again, because the validation happens at the interface of ingesting and storing data for me. And this is our the most common approach in these systems, I think. You have ingestion and validation, and then you store the JSON in some raw storage. It's just a path on the file system. In most systems, I would probably do just hourly kind of partitioning. That is usually good enough. And then when the hour is over, you do some kind of compaction. You probably you have data from 10 to 11, and then at 11, I don't know, 5 minutes after 11, you do your compaction, for example, where you do something with the JSON, because you don't want to have JSON lying around, because it's just a big waste of space, basically. Okay, the alternative is that we do the validation later, not during ingestion, but during the compaction of our data. At least with DuckDB, that kind of means that you have to run user-defined functions, which probably slows down your whole system. But it could be a viable option when your ingestion is not quick enough with the validation to ingest all the data that you are dealing with. We could also do like a step in between. We have like the extra validation step. We write to disk, then validate against the data on the disk, and after validation, we compact our JSON data to Parquet usually, because we want to do, we want to use open table formats because it allows for maximum interoperability. Okay, key takeaways here for me is keep it local first, shift left if possible for validation, fail early if your data is not valid or if your data quality is not what you think it should be, and be as strict as necessary. It's no use to have like bad data in your system, because usually it's not usable in like these types of systems, because bad data usually means corrupted data and not necessarily bad data as it might be meant in like web applications. Okay, let's revisit our ingestion with that knowledge. We do some like minor data validation right at the beginning. If our line is empty, we just continue. We don't want to deal with empty data. There's no use for us. We have the validation here. It's powered by Pydantic, and we write to disk afterwards. So we, like considering the three options I showed here, it's storage option 1, where we ingest and validate and then write to disk. So this is kind of like the data lifecycle we are dealing with here. And we have a source domain we can't change. So the JSON that we're receiving is not like under our control. We have to deal with whatever comes our way. And then we have the Pydantic model that kind of allows our application domain to work with very specific types that we have defined. And this allows us to also deal with like operations we can do on these kinds of types. So far so good. Well, we still have JSON lying around. There's nothing we have done about that yet. We don't want JSON though. However, DuckDB comes to the rescue here. Who in the audience has used DuckDB before? Okay, quite a few people, so I probably can speed up a little bit throughout the rest of the like DuckDB introduction. For all of those for you who don't know, it's basically an in-memory OLAP database. It's sometimes also called SQLite for analytics. You don't need any database server or anything. You just can run analytical queries against Parquet files or JSON files, basically, which is quite useful in many cases because you don't need to set up a Spark cluster, for example. You just can run it on your laptop, and it's quite fast, actually. And for us, it has two main use cases: as a transformation engine between data formats, and in the second step, regarding as a query engine, so we can query our data that we ingested. The compaction that I've been talking about a bit, is basically our transformation from JSON files to Parquet. The goal is to reduce storage requirements, have a better format for our compute, and also increase interoperability with other systems. So DuckDB handles all of this for us, basically, because in one of my projects, I have 3 gigabytes of JSON per hour, and then I compact it to about 300 megabytes of Parquet. So it's like a 10% of the original size, and it only takes 30 seconds on this laptop. And on a server that is very it's not a super powerful server, it's just a very regular one, it takes a few seconds, so it's almost immediately. However, performance, especially regarding the size of your data, is probably depending on how much or what your data looks like. So take these numbers with a grain of salt, and it's more like a ballpark estimate. So DuckDB gives you an interface to execute SQL queries. It's very, very practical if you know SQL. I will omit the DuckDB call for the rest of the presentation because this gives us better syntax highlighting for the SQL queries. So this is now what we're talking. We have JSON, DuckDB in between, and then get Parquet out of this. For this, we need to read the data into the JSON data into a temporary table, for example, and reading JSON data is pretty much as simple as calling read.json in your from part of the statement. The format specifier here says it's new line delimited, so we have one valid line of JSON per line, basically, and not the entire file as JSON. And if we want to write data to Parquet, we just select everything from our temporary table and then say copy to Parquet, and also add some compression parameters, which makes it even smaller. It's super easy to use, very simple, yet super powerful for these like on-prem pipelines. And even better, we can do all of this at once. We don't even need Python, to be honest, because we could save this as a SQL script and then tell DuckDB to run this directly. So no need for Python here. The problem is we still have our JSON files lying around. They're still not deleted. So kind of a bummer here. But deleting old files is where Python comes in. We just call unlink on the path to the file, and it's gone. It's very simple. We wrap all of this in a try except because we want to kind of deal with the errors that we possibly get with file operations. But yeah, quite easy. So, maybe some of you are already thinking, sounds familiar. And it kind of feels like this. It kind of feels like a Delta Lake. Just like ordered at Temu or Wish. So why not use Delta Lake? In my opinion, it's a very viable solution. In Python, it's provided through Delta RS package. The problem kind of is that it only reached version 1 at the end of May, so it was not kind of production ready when these pipelines were built. And it also requires relatively good knowledge about your data, and it's not particularly fond of data changing, and it's kind of hard to deal with that, at least in my experience, although that might be a user error too. So for DuckDB, it has partial support for Delta Lake as of yet. It only supports read operations though, and if we want to write it, we have to deal with something else. Okay, coming to the last part of this, it's analytics. I don't want to dive too deep into this because analytics is very specific on the business requirements, business needs, questions that have to be answered. But usually there's some kind of data preparation involved in all of this. And the data is still around on our on-prem server, and we need to move it somewhere else for business intelligence, for example, to query it. So for analytics, we can also read the data from the Parquet file, just as we did with the JSON file. We can also read multiple Parquet files at once, which is quite useful if you, for example, want to analyze an entire day of data. And then we kind of can do everything that we want with the, what SQL offers, basically. There's only your imagination that kind of keeps you from doing whatever you want to do. But again, this is very specific to the business needs and not something that can be covered here in any meaningful way. But once again, DuckDB is great if you know SQL. So now we have pre-processed our data to clean it up whenever possible. But what are we going to do now? Usually there's some kind of moving to the warehouse. This is quite easy with DuckDB because we can attach different databases or database systems. With DuckDB, we just call attach with a whole bunch of settings. So usually you need the database host, the password, the database name, and stuff like that. But it's quite simple actually, so there's no problem there. And then we basically call insert into, and we load everything that we just analyzed and pre-processed into the database, into the data warehouse, so the database that is kind of attached to that. For example, if you do Power BI, you probably have some kind of Azure database that you want to load it into. So this is kind of what this looks like. We have several Parquet files, and we can do something with them, run SQL queries that are pre-processing this, and then move the results to a warehouse in order to do actual business analytics, business intelligence, for example. So takeaways here, DuckDB is a great tool for running SQL queries. It also can handle a lot of data, in my experience, through out-of-core computing. Sometimes this is a bit confusing because it's called like stream processing or something like that in many tutorials, but it has nothing to do with like stream processing in the sense that Spark, for example, says stream processing. It's more like streaming from disk into our compute engine. For orchestration as the last part, we have a few options. We can use all these regular workflow orchestrators. In my experience, this is also very valid for very simple use cases at least. I probably wouldn't stretch it too far, but getting started, this leaves you without any additional infrastructure. A cron job has very low complexity for straightforward tasks. It's supported by all systems, and almost all orchestration tools have something resembling cron jobs as well. The problem is they're purely time-based, so you don't have any data dependencies between all your like components of your pipeline, which might not be ideal for more complex use cases, but you can always put that into like Airflow, for example, later on. So we haven't talked about housekeeping. You need like to delete old files, move data to cold storage, that kind of stuff. I'm kind of running out of time, so this is why I'm kind of speeding up. We haven't talked about all the DevOps part, so no containerization was discussed, no deployment or observability, but this is really something that you can take from like regular software engineering practices too. And again, the actual analytics, there's no like meaning to discuss this here because it depends on the business. And yeah, key takeaways, I think building data pipelines with Python and DuckDB is quite useful. It scales actually quite well. I've built pipelines that process well over 1 terabyte per day using pretty much this approach. And so thank you, and I'm excited for your Q&A, and if you want to connect with me on LinkedIn or ask any questions, you can use the QR code.
Yeah, so we do have some questions, only 2 minutes to answer them though. First one is, what could be used instead of TCP streams, for example, Kafka or events from a database?
I think you still can use DuckDB for the whole like pipeline transformation stuff. If you run some kind of message broker or something like this, you probably already have a better data format, so all the ingestion gets much easier because you have some kind of schema enforcement before that. What did I do? Yeah, but running Kafka, for example, requires your source systems to also support Kafka at the end of the day, although there are probably some kind of TCP stream to Kafka connector, but I'm not a Kafka expert here, so bear with me.
A second question is what your thoughts on DuckDB not having an auto increment on the primary key of a column?
I haven't had any issues with that. It's probably not as bad for analytics. What it probably kind of isn't ideal for is loading it into the warehouse, because when you see the code, there's a line that basically creates an index based on the data that is available in the data warehouse, and then increments that basically. So yeah, it's not ideal for this type of situation, but in general, I haven't had any problems with that.
Another question is, have you considered something besides Python or for this ETL pipeline for performance?
Yeah, for performance, you could probably use Rust with Nox, for example, for data parsing. I don't see any problem with that. It's usually more like engineering overhead up front, but you have type safety, so you kind of spend something to get something. But yeah, obviously compiled languages are much better in performing like data validation and parsing, for example. So this would be, if you're at the very limits of Python, you probably would go to like a compiled language at some point in time.
Yeah, so the last question is, so you mentioned on-prem, but if you also mention like S3, and so if you are already on the cloud, does it make sense to?
At least in Germany, many companies are kind of wary about the cloud, so they host their own S3 storage with Min.io, for example. S3 is also just kind of basically a protocol, if you want that, even though the AWS service is called S3. But sure, depending on kind of what your overall system and the regulations around it are, you can still use cloud or don't use cloud, but if you're already on the cloud, you could also still do more pragmatic ways than using like all the tools that are available, because sometimes, or quite often, when people or when companies go into the cloud, they go like all in, and there's no sense of pragmatism anymore. It's just kind of, we use the shiny tool, and there's no pragmatic way of doing things anymore. And this is something that I kind of don't like, but generally using the cloud, as I said, I don't hate the cloud. It's fine to use that. Yeah.
Yeah, thanks a lot for your talk and for answering the questions. We don't have time for other questions.
You can also come to me and ask these questions like afterwards. I'm open to answer them.
Awesome. Thanks a lot. So a round of applause.